Hello, my name is Tiago and this video is just a training for my presentations in the Brazilian Power Electronics Conference together with the Southern Power Electronics Conference. The title of my presentation is Enhanced Discrete-time Differentiators for State Observers of Sensorless Permanent Magnetic Synchronous Motor Drives. This is the agenda of my presentation. I will start with a short introduction and the problem delimitation. Then I'd like to tell you about the motivation, the proposed solution. Later I will show you the enhanced differentiators based on finite impulse response filter, which is the main core of this paper. I'd like to describe the principle, the design, and the range of operation. Then I'll show you the differentiators using Kalman filter. And at the end I will show the verifications in the Launchpad microcontroller, this one F28379D, and finally some conclusions. Introductions and problem delimitations. Computing the derivative of a variable is quite common in power electronics applications. In slide mode observers, usually employed in sensorless machine drives, a derivative function is used to compute the estimated speed from the estimated position. In this algorithm, the slide mode observer, at the end of the algorithm we have the estimated rotor position, and then we can compute the estimated speed by computing the derivative of the previous equation. Another example of a derivative function in power electronics applications is in LCL filtered grid-connected inverter, in which a derivative functions can be used to compute the capacitor current from the capacitor voltage. And this relation shows that you can measuring the voltage of the across the capacitors, compute its derivative, then you can have the capacitor current. These have some reasons to do that. This is for resonance damping, and by doing that you may save one sensor. This is a topic for another paper, but in this paper we are focusing on these slide mode observers. However, the derivative function has inherent noise amplification, and because of that some classical and simple techniques are almost never employed, making designers to develop alternative complex solutions. The slide mode observer is an example. This observer is simple and classical, easily to employ in microcontrollers, but it is usually avoided because the derivative function of its algorithm. And also in slide mode observers, not only the noise amplification is a problem, but also the discontinuity found in the rotor position signal. If you take a look at this signal here, this is the rotor position of a motor. This is a sawtooth waveform varying from 0 to 2 pi, but here is normalized to 0 to 1. So we have here discontinuities, and the derivative tends to minus infinity when in the discontinuities, usually requiring a low pass filter at the end of the sliding mode observer algorithm. That's so summarized, we have two big problems. One is the noise amplifications of the derivative functions, and another one is this discontinuity in the input signal of the derivative function. And motivated by the previous statements, I started a research to develop a discrete-time differentiators that work similar to a derivative functions but do not amplify noise. And in this paper, the proposed discrete-time differentiators are to be employed in the sensorless permanent magnetic synchronous machine drives, but of course they can be used in any other applications where a derivative function is necessary. And the proposed discrete-time differentiators may revitalize the use of the sliding mode observers in sensorless permanent magnetic synchronous machine drive. This is one of my motivations, because I know that this kind of algorithm is actually left behind due to the derivative functions, but we try to revitalize it since it is easy to employ, technical, and is really classical technique. And the proposed discrete-time differentiators are based on the finite impulse response filters, and the slide mode observers use the sigmoid function instead of the sine functions. This reduces quite considerably the shattering found on this algorithm. And additionally, we know that the slide mode observer is a technique for high-speed application. For low speed, another technique is usually applied, like the salience-based method. So for low speed, the proposed discrete-time differentiator is based on the Kalman filter. This is quite common also in sensorless machine drives, you have two regions of operations, for instance, one for low speed and one for high speed. So you are going to use one algorithm at the low speed and another one at high speed. The machine starts at 0, and when the machine triggers some value, some set point of the speed, we change the observers to the slide mode observers. So talking about a little bit our proposal, starting with the principle, this chart here shows our idea. So if you see here, there is a line which is the ideal differentiator. This is the S function in the continuous time domain. So you have here the ideal differentiators. If you take a look at this region here at the frequencies in which you have noise, you're gonna see here that there is an amplification of the noise when an input signal is applied to this ideal differentiator. This is what happens in S domain, in the continuous time domain or the frequency domain. But you can design digital differentiators in which you do not have a so high amplification of the noise. And this dashed line here shows that. This is the digital differentiators based on the first difference technique. But when you apply here a digital differentiators, we're gonna see that there is a short region of coincidence. And only on this region actually this digital filter will work as a differentiator. So there is a trade-off solution here in which you do not amplify noise so high versus the region of coincidence. And I'm showing you here this digital differentiator, which is the first difference, as I said, because this is the most used when we have a discretization of an S domain and S function in softwares like MATLAB, Simulink. Most of them are used in rapid control prototype, in which you just place an S function in the Simulink and the software converts to you to discrete time. Usually it is applied at first difference differentiators. And if you're gonna see here carefully, that you see that even though there is a reduction here in this frequency response, the noise amplification is quite high. So design of proposal. The proposal of the enhanced differentiators are based on the central difference, the Hamming differentiators, known as Lanczos and Super Lanczos 1 and 2. These are our proposed differentiators. And the design of them is based on defining a desired frequency response and compute the inverse discrete Fourier transform. With these equations, we can easily compute the coefficients of the filters in which we work as differentiators, each one for this kind of differentiators. Since we have here the complex functions defined by the desired frequency response, we can use the inverse Fourier transforms to get the coefficients of the filter. And this chart here shows now our proposed differentiators together with what I showed in the previous slide. We have here the ideal differentiators, we have here the first difference differentiators, and all of them here are our proposed differentiators. We're gonna see here that we have a low noise amplification in this region. This chart here, for instance, this curve is considerably lower than this, but on the other hand, we have here a short region of coincidence. That's not a so problem because we need to guarantee that our fundamental frequency of the rotor position is within this range of operations, so we can compute the differentiator, the discrete time differentiation accurately. But of course, we need also, if we need, we can increase the sampling frequency. So if you take a look here, the functions that describe these curves, they are sampled in such an amount of points, and computing the inverse Fourier transform, we can get here all the different equations of the differentiators that we are proposing in this paper. This is the phase response. Phase response has not been a problem, even though we're gonna see here some phase delay in such frequencies, but as the result is a constant, we are making the derivative of a sawtooth waveform, so the result is just a constant. So phase has been not a problem in these applications. And of course, since there is a region of coincidence, we need to check the region of operations. So the value of the natural frequency of theta, which is the rotor position signal, must be within the region of coincidence to the enhanced differentiator, thus resulting in accurate processing. In case of such a frequency beyond the region of coincidence, using a high sampling frequency arises as an attractive solution. We computed some suggested range of operations based on the values of the machines that we are using in this paper. But this table here shows, for instance, if you apply a sampling frequency of 10 kilohertz, the region of coincidence will be this one, 0 to 375, which means that the machine can work accurately from 500 to 20 to 2500 RPM. So if you apply a higher sampling frequency, you're gonna see another region of coincidence, another region of speed of the machine. If up to 50K, you're gonna see here that the machine can work at 10,000 RPM accurately, and the discrete time differentiator is computing properly its function. Of course, this region of operation is for the are valid for the machine used in this paper. So another proposed here is the differentiators using the Kalman filter. So this is the algorithm, classical algorithm of the Kalman filter, the second order algorithm, in which you have here the input signal and the output signal. The output signal here is a vector in which you have the first one is just the input filtered, and the x2 here is the derivative of the first variable. And since we have a sawtooth waveform, they are actually valid for low speed. It is actually easy to model such a signal, so we have here the matrices used in the Kalman filter algorithm. Verifications in the F28379 Launchpad microcontroller. All the differentiators proposed in these previous slides were programmed into this Launchpad. Additionally, a real-time simulator HIL 402 from Typhoon HIL was used to run the model of the machine. The rotor position is sent from the HIL to an analog input of the Launchpad. The waveforms of the rotor position is a sawtooth, vary from 0 to 2 pi. In order to check the efficacy of the differentiators, the theta signal was intentionally polluted with noise, and therefore the performance of the differentiators are presented with and without noise applied to the theta signal. The output signals of the differentiators are externalized from the Launchpad through its analog output and visualized in the oscilloscope. These are the parameters of the system. I'm gonna take a care look later in the paper, but just showing here some parameters of the machine and taking special care that we are using a sampling frequency of 10 kilohertz. Starting with the first differentiators and the machine running at a 600 RPM. This is the most classical differentiators using rapid control prototyping. So you're gonna see here the sawtooth waveform, the rotor position with no noise, but you're gonna see that the derivative of that signal has this minus infinitive variation. When we apply noise at this signal, you're gonna see that the result is quite messy, it's quite not good. Moving to the proposed differentiators, starting with the central difference in the same condition. So we have here that we're gonna see that in the discontinuity we have a much lower variation. When we apply noise, you're gonna see that there is a kind of ability to not to amplify such a noise, and you're gonna see a result very similar to the case in which you don't have noise. Moving to the Lanczos differentiators, you're gonna see here that there is now beyond the ability of not to amplify noise, also the ability to have a lower transitions during discontinuity. This is good because we may avoid using a low pass filter later after this is computed. For the Super Lanczos 1 differentiators, also running at such a speed, you're gonna see here similar behavior, same kind of ability to deal with noise, but we have here kind of not so good variation during discontinuities. For the Super Lanczos 2, similar, we have a quite similar behavior. I'm gonna see here for the noise, and without noise, I'm gonna see this behavior. And just comparing another scenario in which we compare the central difference and the Super Lanczos 2 differentiators when the motor speed is at 4000 RPM and with noise. So we have here now, remember that we are sampling at 10 kilohertz. So we have here the input signal with noise. We're gonna see here during the transitions the differentiator has this kind of behavior, but for the Super Lanczos 2 we're gonna see that there is here much more flat output, also indicating that maybe we can avoid using a low pass filters to compute these variables in the control. And to finalize the verification, now the common filter differentiator is running at 2 RPM. Now the machine is working as kind of a servo drive, which is a very low speed. So we have here such a behavior with noise and without noise. With noise, we're gonna see such an ability to have this pattern similar to this, but of course we have some problems here in the discontinuity to which you have a high transition. Conclusions. Results show that the proposed enhanced differentiators had good abilities to compute the derivative of the input signal even in the presence of noise. The Lanczos differentiators show the best solution in terms of behavior during the discontinuities, making possible avoiding a low pass filter. Of course, there is a trade-off solutions between region of coincidence and noise amplification. Therefore, the proposed differentiators are attractive solutions to be employed in stage observers of sensorless motor drives. And besides that, they can also be used in other applications in which a derivative function is necessary. I'd like to thank you very much to the FAPESC, in which granted this project, and also the state of Santa Catarina government. Thank you very much. If you have any questions, I'll be so glad to answer.